So the first talk, let's start with this Trapeze Artistry in Biomimetic smart gels. I must say that I was very privileged to receive the World Academy of Science Lenovo Science Prize 2019, and I had to deliver a lecture when I received that. And the lecture was titled exactly the way this lecture has been titled. Excepting that, because there are a large number of students here, I'm not just going to talk about the science that went behind it, the what of it, but the how of it, in terms of the way we went there, so as to say, because maybe some of these lessons would be useful. I want to begin by the journey. You will not be able to recognize, but this young man is Ramesh Vishalkar. This was 1976. And I came back under very interesting circumstances because the Prime Minister of India then, Mrs. Indira Gandhi, she was very worried about the brain drain. And she was very worried about the bureaucratic processes when scientists came to get a job was so difficult. And that was roughly the time when Khurana, who got Nobel Prize, he had come to India, didn't get a job, went back and got a Nobel Prize. So there was big discussion. So she said the best way to get young people back is just go and invite them and get them. That's it. No interviews, nothing, basically. So among the selected few, I was one of them. And I was barely 33, and I took a decision that I'll basically come back. The interesting part I want to emphasize is the India then was very different from the India now. 32K was a big memory. We used to share a 128K machine with University of Pune. The journals used to come by sea mail. They would take 3 to 4 years. I was trained in rheology and non-Newtonian fluid mechanics. We have a master here, Tam Sridhar Ravi here, they will know. And there was a Weisenberg rheogoniometer I needed mark, and it took 2 years to come, basically, because no foreign exchange, DGTD clearance, not manufactured in India certificate, etc. So those were the conditions under which we actually did research. I think it's very important to show here National Chemical Laboratory. Some of you have visited it. The purpose of this laboratory has been defined as you enter this laboratory, and so beautifully defined. It says the purpose of this laboratory is to advance knowledge and to apply chemical science for the good of the people. Just think about it. Advancing knowledge and using it for the good of the people. You can't have a simpler statement, you can't have a more powerful statement. That's what we were actually supposed to do. And my mandate was to create a polymer science and engineering group which didn't exist. And within that, I remember one of the first things we did was to create a very interesting polymer. And here you can see its demonstration. This is a pinch of a polymer. And you see a lot of water being poured in, getting stirred, and the polymer is super absorbent. It absorbs all that water. And as you can see, you can tilt it over, and that's it. It just holds that water. Now, these are called super absorbing polymers, and there is a deep science as to why they super absorb. But we were interested in the application of this because, as it said, use it for the good of the society. So what good is that that we can do for the society? Now the developed world, of course, had its applications. For example, the baby diapers, retain water in the diaper when the baby urinates, or sanitary napkins and so on and so forth. But in India, we had a different challenge. And that is this, that is retaining water in soil in a parched land, for example, was a big challenge. Retaining water around the germinating seed, because the rains will come and then they will not come for a week. Then what happens to the germinating seeds, basically? So we developed this polymer, hydrolyzed starch grafted polyacrylonitrile with the water absorption capacity of 200, 300 gram per gram. And this will be used for seed coating, soil applications, and so on and so forth. Of course, we had to do extensive trials. The Indian Council of Agriculture Research actually did trials all around the country to see what were the benefit, the cost, the biodegradability issue, and so on. And you can see some of the results here. They are variable, as you can see, depending on the crop, depending upon the place where the tests were done, and so on. The idea finally, of course, is it has to be in the hands of the farmers. It was brand named as Jala Shakti, by the way. Jala is water and Shakti is power. The power to hold water, basically. That was that. And remember, going into the manufacturing process, we licensed it to a particular company. And these are small, like you have mom and pop shops here. We call them Kirana shops. And Jal Shakti was sold all over the country, basically. And you can see the farmer, he is being explained the way it can be used and the benefits it will have, and so on and so forth. So finally, it's not just any use developing a product and showcasing it in the laboratory, but finally it's in the hand of the farmer that actually mattered. So I go back to what National Chemical Laboratory said to us: advance knowledge and use it for the good of the people, by the way. Now, applying science for the good of the people was one thing, but advancing knowledge at the same time was quite another. And that is where we got interested as we started looking at these super-absorbing polymers. We said the water-soluble gels are mundane, like Jello. But if you look at water-soluble gel with life, like a sea cucumber, it is nothing but a water-soluble gel. It is able to feed itself, reproduce, defend itself, it stiffens on touch, and as you can see, if it is removed from its aquatic home, it even expels water, so it reacts basically. All right? So how do we put life into gels? That became the sort of scientific exploration, the scientific ender. And we are not the only one. There were many who were doing it. People had shown how gels can be made sensitive, how they could have shape memory, how they can have mobility, and so on. But what you see at the bottom are things that we did for the first time, showing that they can be self-organized, they can be self-healing, they could have enzyme-like activity, etc. And I'll come to that in a moment. And what is very special was, of course, that these gels show volume phase transitions. For example, you can see the two equilibrium states. On your left-hand side, you will see the collapse state. On your extreme right, you will see the solid state. And in between, you will see a state where the two states coexist in equilibrium. And just 1 degree switch of temperature, basically, can change the swell. All right? So if 12 degree is the volume phase transition, at 11 degree it is fully swollen, and at 13 degrees it totally collapsed. Okay? So this is the feature that we had. Now, this was used actually in creating shape memory in gels. For example, there is a paper in Science where you can see a pentagon can be converted to quadrangle, and quadrangle to a pentagon reversibly just by switch of 1 degree sort of centigrade. So that was shape memory. See the mobility. For example, we are always talking about robots. But robots have sort of hard fingers, so as to say. Can we have soft fingers? And that sort of work was being done in Toyota Research Center, for example, by creating what is called as the axisymmetric bending by using bigel strips, so they showed mobility. Now the interesting part is that if you see, the early breakthroughs came in US. Professor Tanaka from MIT was the master who actually showed these volume phase transitions. So you can take a small sphere, put it in water, it will become a big sphere, and reversibly can collapse and go back. So if you have a small cylinder, it will become a big cylinder and collapse and get into a small center. That was the work. The Japanese in mid-90s actually did the bending part of it, basically, by using sort of variety of means, including the Biomimetic. And the breakthrough that we had in NCL was that a cylinder could be converted not only a sphere, but a coconut-like structure. And that could be done reversibly, by the way. In fact, nature called it Indian rope trick, by the way, when this paper was actually published. I must say, the work by Tanaka was organized research. All right, it was not serendipitous. The work in Japan was organized research. It was not serendipitous. I must say, NCL was lucky. We were lucky. We got it as an accidental breakthrough. And I'll come to describing that a little later. I think the real challenge that came up was the following. I remember being in Boston in 1993, where the basic issue was that I had written, I had given this Dankworth's Memorial Lecture called Seamless Chemical Engineering Science, because the boundaries between engineering and science were engineering. And it became a big talking point. Bob Brown at Chemical Engineering Division, later on he became the dean and then the president of Brown University. He was member of the Chemical Engineering Science Editorial Board, and he had a big meeting in Boston to discuss about this borderlessness and how do we move forward. And lots of people participated, Bob Langer and so on. In the meantime, we were doing a lot of good work on gel, good science was being published. So the gel science technology company, Boston, they invited me as a consultant. And they posed a very interesting problem to me. The problem is here. They said, can we design a smart soft gel that can conform to the shape of the foot? Why? Because when you have a diabetic foot, basically, your ulcers, your sores, and so on and so forth. So in this particular case, what happens is the temperature variation from tip to toe is around 5 to 6 degrees centigrade. So supposing you create sort of a gel which expands and contracts or undergoes a transition, volume transition at that specific temperature, then you can conform it to the... So we are talking in terms of a smart sole in basically a shoe. That's the challenge that they gave, as a matter of fact. What it meant was that a field which was ridden with empiricism, they were asking us to do molecular tailoring to get precisely 32 degree, 31 degree, 35 degree centigrade temperature, or 29 degrees, and so on and so forth. And that is the challenge with which we actually started. That was the trigger. So I think the story that I'm going to narrate to you in the next half an hour actually tells you about how we created the first molecular basis. And in that, the tightrope trapeze artistry, how did it emerge? And I'm deliberately emphasizing, particularly for the benefit of the students, that there was some part of it, as you can see, molecular tailoring was organized research. We had to use known tools, theoretical tools. But the anomalous macroscopic self-organization and unusual self-healing that we observed was totally serendipity. It was accidental breakthrough. But the discovery of master trapeze artist, acrylyl 6-aminocaproic acid, as I will talk about, was organized research. So it's a combination of the two. You know, science is never linear. I mean, there are lots of things that happen. And then finally, I will describe the magic of A6 ACA as to how it has caught on and caught the fancy of the word. To start with, the molecular basis for VPT. People were using this Flory theory of swollen networks. Tanaka, for example, used to modify this Flory equation, which was very famous empirically. But the problem was that the differences in compressibility, the specific interactions, etc., were actually missing. So the molecular interactions were missing, and this lattice fluid hydrogen bonding model, I wouldn't have time to get into the full detail, was something that we had to go to in order to ensure that we incorporated the hydrogen bonding, we incorporated the hydrophobic interactions, the entropic elasticity, and the rest of it in order to give it a sound sort of molecular basis. The experience, of course, is amazing when the theory fits the experiments. And as you can see, we had this N-isopropyl acrylamide as a molecule, and this is very interesting because this is the amide group is hydrophilic, and this isopropyl is hydrophobic. So in the same molecule, you have both hydrophilicity and hydrophobicity. So the amide can interact with other amides hydrophilically. The isopropyl will have hydrophobic interactions with sort of other groups. And interestingly, you can see the theory and experiment matched very well indeed. And we got, of course, interesting insights. For example, at the transition temperature, we found that the interpolymer hydrogen bonds per chain increase abruptly, whereas the polymer solvent hydrogen bond chains decrease abruptly. The interesting part was our finding that this interaction parameter, the zeta, had to have temperature dependence, and particularly decreasing zeta with increasing temperature implied increasing hydrophobicity. This was an observation that we made while doing our theory, by the way. There was no experimental evidence on that. But interestingly, this experimental evidence came in a PNAS paper by Lee and Walker later. As you can see, this is a stage coil global transition of polystyrene from a globule stat, and you are staging the polystyrene molecule, and you are measuring the force. And as you can see, as the temperature increases, the force starts sort of increasing. So this was the first indication that what we had deduced in 1995 was right. And there are some other evidences also. The most important part I want to emphasize, however, is that when we started playing around with our model calculation, there were two things that became important. The first was, in the model, if we put the absence of temperature hydrophobicity, you did not see any transition at all. If you knocked out the hydrogen bonding, you did not see any transition at all. But if you put only both of them, then you would get them. We were the first ones to actually bring out that both this hydrophilicity and hydrophobicity, and that is where the trapeze artistry started actually coming in. And as you can see, this is the trapeze artist. So what one is trying to say is that you have to balance out, and if you don't balance out, you lose out, so as to say. And how did that balance get created? Of course, life already knows that. I mean, if you see, the integrity and function of cell membrane is governed by the hydrophilic and hydrophobic balance of phospholipids. As you can see here, the phospholipid bilayer, the hydrophilic head and the hydrophobic tail, and this delicate balance actually retains the cell membrane structure. And the moment it gets disturbed, as a matter of fact, you have the disruption of cell membrane leading to sort of cell death, because that controls the substrate intake and sort of outtake. So nature already is always ahead of us, by the way, in terms of doing this particular artistry. Let me then get to the tailoring of the volume phase transition, organized research as I call it. So we started playing around with it, as you saw this transition. So we had this polyintercyl-butyl acrylamide, which is hydrophobic monomer, and you have it copolymerized with polyacrylamido-methyl propane sulfonic acid, which is hydrophilic. So hydrophobic and hydrophilic. And see this very carefully. What you see here is that if you have a total hydrophilic monomer polymerized, you have no transition. You have a total hydrophobic monomer polymerized, you have no transition. But when you make the combination of the two, you see the sudden transition. That is the balance, the hydrophilic and hydrophobic balance, which actually gives you the transition. This is experimental. So what it actually showed was that the hydrophilicity increased, the hydrogen bonding increased. You could shift the transition temperature, and as hydrophobicity reduced, you can reduce the transition temperature. So what it means is that for the first time now, your handles on what are the factors at a molecular level which actually control the transition temperature. Otherwise, it was all empiricism. So we had put sort of torch of light. So therefore, I keep on getting back to the smart shoe sole challenge that we had. They wanted us to do the molecular tailoring, but for molecular tailoring, we need to have certain sort of exactness in terms of what we do. We went into further experimental validation, and this is the most important part. We have the N-isopropyl acrylamide co-polymerized with acrylyl amino acid here. And what is most important is this part. This is the methylene group. This is the hydrophobe. And the number of methylene groups you can change from 3 to 5 to 10. All right? So the hydrophobicity will keep on changing as you increase the number of alkyl groups, basically. So this is what we actually played with. And the experiment showed to us something very interesting. In fact, we saw that there can be a precise control of volume phase transition by varying the methylene groups. In fact, there was a 2 degree centigrade change with every addition of a methylene group, basically. This was experimentally found. What it means is that we are getting closer even to the smart shoe sole challenge in terms of actually molecular tailoring and designing. This was done for the first time. And we had some other interesting things that happened. We found, for example, that metal ion complexation also could produce that. For example, if you see the uncomplexed part of it, and then complexation, how it changes, and it is obvious that the metal complexation actually will increase the effective hydrophobicity because it will lock in the carboxyls, so as to say, making it hydrophobic, and that will decrease the transition temperature. So there is one more handle. So what am I talking about? I'm talking about controlling hydrophobicity or effective hydrophobicity by changing the methylene groups, putting in sort of metal ion, and so on and so forth. So there are different handles that you start actually having. Now, while we were doing that systematic work, I must say that there were 2 serendipitous things that happened that helped us progress. And if those accidents had not taken place, very frankly, we would not have progress. Now, here is a very interesting story, Alan. You know, I talked about lack of resources. Can you imagine our group at that point in time? We wanted to dry gels overnight, following a protocol. And there was money only to buy one new oven. So my student, Shiny Varghese, she had kept gel piece in the oven, which was translucent. Okay? Following day, she opens up and finds it's not translucent. It is not even cylindrical. It is spherical or ellipsoidal, and the color is blue. So she thought that somebody must have, because there are lots of pieces that are kept there, no? So somebody must have messed up and so on and so forth. So following day, there was always a queue. This is how research is done under constrained conditions. There is always a queue. So she finally got her turn to keep it in a clean oven. So she put a translucent piece. Following day, in the morning, it was translucent, no change. So in this oven, it turns blue, and in this oven, it remains. Now, here is the serendipity, and here is the accident, and yes. So she was so determined, by the way. She was one of my, I would say she was my best student, by the way. She's a full chair professor in Duke today. Outstanding girl. So, you know, Elizabeth, what she did, she stayed overnight and kept on watching it. And then later on, she realized that when she was shutting the door, Ravi, because it was corroded from inside, the iron pieces were falling on the gel, basically. So that ion complexation was actually making the trick, basically. She found that. But then the basic issue is, and by the way, we are not the first one, just want to remind you that Charles Goodyear in 1839 dropped molten rubber and sulfur accidentally on a hot stove, the piece of solid workable cross-linked rubber, exactly what he was looking for 10 years. And had he not done that, we would not be having rubber tires, by the way. So like in our case, the iron piece foil was gel. In his case, you know, this particular accident took place. So we have to be humble that this happens sort of all the time. The basic issue was why should a cylinder turn into a sphere? Okay? Why should it change color, but what it should turn? So we actually watched what was happening by taking sort of cross sections, so as to say. So not only it turned into a soft sphere, but later on it turned into a coconut-like structure. And we discovered, after doing sort of more detailed analysis, that it can happen also along with other cylindrical gels formed with other transition metals like lead or cadmium or zinc. And in fact, you can see here that cytophores, for example, did this self-organization 100 nanometer. The coconut did it at 10 centimeter, but our gel was intermediate, macroscopic self-organization, so as to say. Now the question is, why does it happen? So when we did the analysis, if you see the hard core outside, followed by a softer inside. So what happens is, you have this acrylyl 6-aminocaproic acid polymer, you put it in copper chloride solution, the cupric ions start diffusing, basically, and at the interface, they lock in all the carboxyls, which are hydrophilic. So if all the hydrophilicity is knocked out, you have a hydrophobic surface. So you have a cylinder with a hydrophobic surface in water. So what does it do? It tries to minimize its surface energy. And what is then the form? It has to be the sphere with the list. So it turns into a sphere. But why the hell should it convert into a coconut-like structure? Now there's a mechanics there, because then the cupric ion that basically comes, we found out that when you did the analysis, there are two species, the monomeric as well as dimeric, basically. When the statistical probability of two cupric ions coming together, then it becomes a dimer, basically. And these dimers are tightly squeezed, so as to say. So now you can imagine the diffusion process, tight squeezing, basically, and then creating a rupture, so as to say. And that is what, of course, we verified by taking the EPR spectra on the presence of sort of both these. So now you have a very nice system that you can take a cylinder, convert it into a hollow sphere. So what? And this is interesting, sort of as an observation, but engineers always think of an application. So we said, well, maybe we can use it for innovative controlled release devices, like hemoglobin release. As you can see, it's a sort of constant release that you can obtain. Gel reactors, catalysis. In fact, we did an experiment which was very interesting, the synthesis of quantum dots. This was done in 1998, almost 12 plus 19, 31 years ago. And you can see the complex gels subjected to H2S gas. They showed formation of cadmium sulfide quantum dots. You can see the larger quantum dots in the core and smaller in the shell, depending upon the monomeric and dimeric species, as a matter of fact. Unfortunately, this work we did not pursue further, but you can see how long ago this was done. So this was one, let us say, serendipitous observation which gave us some new science. The other one was like this. Engineers are always in a hurry, because this swelling, deswelling used to take hours, and we say not hours, minutes. So how do you say not hours but minutes? It's like a piece of sugar. You put it a big piece of sugar, it takes time. You keep on grinding it, make it fine, and it dissolves quickly. So reduce the size. That is what we said, and kept on reducing the size. We said that 1/100th of the time will be taken, if we had small size, and basically we'll take the dry gel, we'll grind it to fine powders, fill it in copper chloride solution, but we'll always get a lump. They will be always sticking together, and this is a scanning electron microscope sort of study. So therefore, this was a failed ACM, so as to say. That means we'll recognize this as a failed experiment, so as to say. But you know, there's a beauty there. The beauty is the two surfaces are healing. And how can gels heal? Because a gel is a macromolecule, single molecule, large giant macromolecule. You know? If you take, for example, you must have done all this, you know, I mean, you take a film and you want to seal something, you hit it a bit, put the iron on, and then why does that happen? One piece of polymer, another piece of polymer, you bring them together, put them over the glass transition temperature, and then reptation across the interface, and you have welding. But not so in the case of a gel, which is a big sort of macromolecule. Why? Because the center of mass diffusion is rendered impossible due to the pinching of chain segments. So we had to think afresh. That was not a failure. It was a success, accepting that there are different mechanisms that were operating. So for my young students, when you see a failed experiment, by the way, there is a message in that failed experiment. You call it a failure because it does not meet your sort of normal expectation, but there is some mystery there. And I think it is extremely important to learn to unravel the mystery of the failed experiment, because each failed experiment has a breakthrough in it, as a message in it. In fact, those of you who are interested, there's a paper I have written, Fun and Joy of Science, Learning from Anomalies and Discontinuities. And in my personal life, I mean, there are a number of other things that we have done, basically where we have come to new science as a result of this. So the explanation was that the initial welding takes place by the coordination of the cupric with the carboxyl of the flexible child chains. This swelling then is combined with macroscopic deformation, which enhances the weld line strength, and then a single welded gel piece that is hollow from inside. And in fact, the weld line has enough strength to sustain the stresses that are created during the formation of the hollow interior, that is the pieces. We took this forward, by the way, without cupric iron, and you can see a beautiful experiment here. The deprotonated A6ACI hydrogels. You bring the two pieces together, instantly they healed. And you can see they are stretched, and yet they sort of withstand that stretching. So therefore, and this was a paper we published in Proceedings of National Academy of Science, the healing mechanism is like this, that when you have a large pH, for example, there is an electrostatic repulsion between the deprotonated carboxyl groups. Then you lower the pH, there is a protonation of these, and then if you see the interweaving of the two chains at the interface, and then the hydrogen bonding between them, and that is how the healing actually takes place. Okay? Or in other words, if you go back to pH 10, you will, whatever has healed will disappear, and if you lower the pH, the complete healing will take place. So it's a reversible process that you see. And it's extremely rapid, so as to say. Now, this is where the discovery of the master trapeze artist came up. Because we kept on doing these experiments, by the way. We also did some very advanced sort of molecular dynamic simulations, which you see here. And the basis was that as we kept on playing around with the number of methylene groups, if you had just one, there was no healing. 3, no healing. 5, strong and rapid healing. 7 was weak, and 10 did not heal. So if you had too small numbers, it did not heal. Large numbers, it did not heal. But there was a magic about 5. That means acrylyl 6-amino caproic acid. Okay? Now, this paper also told us that if you have too long a chain, it folds onto itself, so as to say. If you have too short a chain, it is not able to search out. So there is a optimum balance and interleaving. That is what we saw by the molecular dynamic simulation. So this acrylyl 6-aminocaproic acid came as a result, first of an organized research to find out what the theoretical interpretation of this is, then the accidental breakthroughs that we had, then a systematic study, so as to say, and then we arrived at this decision. Frankly speaking, at that point, we thought, that's it. We published a paper and we were very happy. We never knew what will happen to that A6-ACA, acrylyl 6-aminocaproic acid. And it is unbelievable. The magic of A6-ACA has been felt in vast diversity of fields, basically. And I will just very quickly sort of illustrate to you what it is. Now, Alan, this is what is very interesting. We keep on collecting the dots, that is, collecting information. A little bit the important part, like we were discussing, is connecting the dots. And particularly if you start connecting the unrelated or seemingly unrelated dots, you get breakthroughs. In fact, this is what mathematician Poincare had said. The useful or interesting combinations are those who reveal to us unsuspected kinship between the other facts, long known but wrongly believed to be strangers to one another. Accordingly, among chosen combinations, the most fertile will often be those formed of elements drawn from domains which are far apart. So A6-ACA, when we came, we never thought it will be used in kind of different domains that we had not conceived. In fact, what Heraclitus had said 500 BC, the unexpected connection is more powerful than the one that is obvious. And how do you make these? I don't know, Alan, whether AI has the power to do that. In drug discovery, they are trying to do that now, for example, using AI. And, you know, if you know the pathways, can a molecule that has been discovered for something can be used for something else, and so on and so forth. But the basic point is this is very, very sort of important. So the magic was felt in many different ways. There were studies that have been done where the interfacial engineering to promote cell adhesion, shape, migration, and differentiation has been looked at. And they created matrices of different hydrophobicity but similar bulk moduli. And they were engineered, and the length of the spacer group was changed. And if you can see very clearly that C5, that means acrylyl 6-aminocaproic acid, is the one where there is maximum adherence. But if you see the others, for example, it is much less indeed. So there is something very interesting that is happening here. If you see, for example, the way the cells adhere and spread, they spread based on A6-ACA. If you see the fraction of adherent cells, C1, C2, C3, C4, C5 is actually the top. And if you see, for example, the cell surface area, again, it is C5 which is the best. So A6-ACA somehow or the other seems to be doing the magic. If you see here, stem cell move much more slowly on surface containing C5 side chain, that means acrylyl 6-aminocaproic acid, than the C3 side chains. And if you look at the adhesion force on cells mitigating, C5 is actually the highest. We would have never imagined when we did acrylyl 6-aminocaproic acid as a result of our polymer science work that this will have some say in terms of this issue. The other one was this hydrogel biomineralization, the dangling side chains, and you can see the kind of biomineralization that takes place with calcium phosphate, which is very critical. And you can see, for example, the fold expression. If you look at the mineralized one versus the non-mineralized, non-mineralized is blue, and mineralized is green with A6-ACA. You can see the maximum with the mineralized one. A real breakthrough, as you know, Bob Langer is considered as a kind of a big star. He got the Queen Elizabeth Prize of Engineering. His work in biomedical has been sort of recognized all over the world. And his group got interested in A6-ACA. What was their problem? Their problem was they wanted to create gastric retentive devices. That means you take it inside, it passes through your stomach and then into intestine. And stomach is highly acidic, so it should stay. And then it goes into alkaline, and then sort of it should release. All right? That is the requirement. So gastric retentive devices must have facile delivery for prolonged days, gastric retention. And the existing enteric polymers were rigid and brittle, so there was a big challenge. And no device for combining enteric plus elastic properties. So they found a solution. They said, why don't we create a pH-responsive supramolecular gel, stable in acidic condition, gastric pH, but dissolvable in alkaline condition. And you know finally who the winner was? A6-ACA. They created this supramolecular gel, as you can see here, with polymethacrylic acid co-ethyl acrylate as a copolymer. You can see its elasticity. Basically, they have stretched it, and again, it's sort of bring back. You can see the stress-strain curve. You can see the dissolution characteristics. You can see the ring-shaped objects that they pushed in, basically, and its gradual dissolution. What is most satisfying to me is that this particular statement that Bob Langer's group has made. It says, although there have been extensive studies and commercial examples of gastric retentive devices since the 1970s, this manuscript presents the first demonstration of both extremely prolonged gastric retention and safe gastrointestinal passage with the help of this innovative combination of elastic and enteric properties contained in one material. That's very satisfying, basically, because he's the master. If he says that, there must be something. But Elizabeth, when we were having that accident in our poor laboratory because of the rusted oven and so on, we never knew that the result of that will be finally creating something that is the best that is said after 90 said. Another amazing application, Mark, here, Halliburton has done it. This is about the oil well drilling issue, because there is a loss of circulation fluids in drilling wells. It's a very common problem. So they use a lot of materials, inorganic, polymeric, etc. So what they did was to introduce these PA6ACA hydrogel particles in order to do the block. And the way it worked is very simple. Because we saw high pH, they will be segregated. You lower the pH, they will be aggregated. You go to high pH, they will be again segregated. Okay? So what it means is that just by switch of pH, you put a suspension, switch of pH, it will do complete sort of blocking. Okay? So that's another very interesting application. Now, what is happening is that this has attracted such an attention that now everybody is getting hold of A6-ACA and trying to see what better they can do. So, for example, they have taken graphene oxide and again bonding it with PA6ACA, mixing 2%, and they find the tensile strain goes up by 7.3 times, elongation by 3 times, and they heal very rapidly. So they are now moving their physical mechanical performance in another region by getting into carbon oxide. There's a lot of work that is going on in Japan, by the way. Then they have also done the carbon nanotubes. Again, something similar. You can see sort of a major change that takes place. The XRD data shows the kind of bonding you have, and the strain by 7.3 times, elongation by 3 times, very rapid healing. The CNT, the carbon nanotubes, again, something similar. I'm just giving you a few examples, there are more. But I think the point I'm trying to make is that the diversity of fields, basically whether it is stem cell research, whether it is oil well drilling, whether it is biomedical devices, etc., is really sort of spectacular. We would have never imagined that. Let me end by going back to what I said. I told you that sensitivity, shape memory, mobility, others had done. Self-organization we discovered. Self-healing we discovered. That was accidental. But I didn't tell you about the enzyme-like activity because that is a full lecture, as a matter of fact, so I don't want to sort of give it. But very quickly, the trigger again, like, you know, it was a consultancy challenge. This was also a consultancy challenge. I was a consultant to Unilever, and they had laboratories in Port Sunlight, in Flardingen, Edgewater, and so on and so forth. So I was in Flardingen. And we were talking about the metabolic pathways, you know, in the sort of enzymatic reactions and the modeling and so on. And they said it would be wonderful if we had enzymes which can be switched on or off at will, basically. So that in the entire pathway you can do selective switching in order to get the kind of products that you want. And we followed a strategy of switching. We did the enzyme, we took chymotrypsin as a model and did the mimicking through some good chemistry. And I'm not going to go through the full detail because there will be a dozen slides, but I can show you the results on how, for example, we were able to photoreversibly on off the catalytic activity by turning the UV on or off, and matching with the model that we had, by the way, and same thing with regard to pH. The issue was that here was again a challenge. Coming in a consulting sort of role that I had, and asking for solving a problem that needed to be solved, so as to say. So let me end, this is my last slide, by saying a few words about the lessons that I have learned in my life, and maybe some of them will be interesting for you. The first is going for problems that need to be solved rather than that can be solved. And that can lead to breakthrough science. Because normally our challenge is excellence and relevance. We say, oh my God, this is so relevant, it can't be excellent. All right? In our academy, and I've been associated with academy, thanks to two of you, for so many years now, we have been having industry partners as knowledge partners, basically, and trying to look at problems that need to be solved rather than that can be solved. The purpose is here. And you could just see, my Unilever consultancy got us a scientific breakthrough because they asked a question, can you switch enzymes on and off? My jail science consultancy, they said, can you tailor, let us say, the shoe soles smartly, basically. And that came to a huge new knowledge. I'd done something else also where we had got a breakthrough on how inertia can be damped, and inertia and viscoelasticity play a role under laminar conditions to do the damping. We had a paper in Nature. So my own experience has been that these are wonderful partnerships which can actually give you breakthrough science, some of which I have demonstrated here. That's the first part. That's why in the academy we insist on building these relationships. The second is connecting the dots more important than just collecting the dots, basically. You could see the kind of diversity of applications. And that requires a special mindset, by the way, so as to say. The next one is that in science, being the first to open a new window is far more satisfying than merely looking through windows that others have opened. And we often do that. Somebody has a breakthrough, Bednorz-Müller have a breakthrough on superconductors, and then all of us work on that. Somebody has a breakthrough on carbon nanotubes, then all of us work on that. Somebody has a breakthrough on graphene, we all work on that. But when will we create our own graphene? So therefore, they say in science only two people are remembered, the one who says the first word and the one who says the last word. So therefore, I'm happy that as you can see throughout the lecture, there have been 7 or 8 places where we have been able to say actually the first word. So that has been very satisfying. And that is where we come to Sir Alan Finkel criteria. I hope you have read his Nature fantastic paper on quality matters, not quantity, and his rule of 5. He doesn't want you to give all your 37 papers. He wants you to give only 5 papers, where you have made a difference, basically. I think that's a very, very important Alan Finkel principle, which I love. And Alan, I can give my 5 papers, by the way, which have made a difference. The next one is that serendipity smiles only on the prepared mind. Okay? Eyes do not see what the mind doesn't know. So how do you prepare a prepared mind? I think that's what we have to actually learn. Because look at the failed experiment very carefully. Maybe the next big breakthrough is waiting there. And from my personal life story, from India in those days that I talked about, when 32K was a big memory and it took a couple of years to get an equipment, etc. I would simply say it is the size of the idea that matters and not size of the budget. Scarcity coupled with high aspiration, and Alan and I keep on talking about high aspiration, that can be an explosive combination. Our challenge, as my Guru C.K. Prahlad used to say, here is the aspiration and here is the resource. As the resource goes up, the aspiration keeps on coming down. The challenge is how to keep the aspiration high. And under those poor conditions, we keep the aspiration high. And that's why I'm able to stand before you and actually make this particular presentation to you on our journey, an exciting journey, I would say. Thank you.
So I think we do have a few moments for questions, so I'd open up the floor.
So really nice talk, and when you said the thing about the good luck, I guess obviously you make your own luck. But I wanted to ask you about the question about the agricultural application at the beginning. When the seeds get coated, does the soil properties, do they change as a result of the presence of those seeds? And I'm just wondering, like for the next season, would it be, with the property of the soil, so it would retain more water and so forth?
Yeah. Here we are talking about seed coating.
Yeah.
Seed coating by definition implies a very small fraction, so as to say. Okay? Because the idea is the rains come, okay, and then they don't come for 7 days. So when the rains come, the seeds start germinating, and then it is deprived of water. The coating, by definition, is a small amount, basically. So that picks up water, which could be 200, 300 times its weight, and keeps on supplying it to it. So the number is small. Secondly, in those applications where it is used in large, the trials have been done, because we created not the polyacrylic acid, the sodium salt or potassium salt, which is used in diapers, but starch-grafted polychloride. So there is a rapid sort of biodegradation, so as to say, within the soil. So there has not been a perceptible change as far as that is concerned. ICAR, the Indian Council of Agriculture Research, has looked at it very carefully. Yeah, that's a good question, because see, formally it has to break down into the constituents, carbon, nitrogen, and oxygen. There are no other sort of compounds. If you look at the polyacrylonitrile hydrolyzed. Yeah.
You finished off, thank you very much, talking about quality in research publications, and I was thinking about research publications when you gave that picture of the experiment with the new oven and the old oven, where you didn't get the change that you expected in the new oven, but you did it in the old oven. Basically, it was a failed experiment. And you were lucky, because it was in your institute,